In this third section of 4.2, we'll talk about the basic difference between fission and fusion. Everyday chemical reactions show us that mass is conserved, but in nuclear reactions, both energy and mass can be converted into each other. It has been determined that the mass of the nucleus is always less than the sum of the masses of the individual protons and neutrons that comprise it. This is called the mass defect. So how do we explain this? The missing mass provides us tremendous energy required to bind the nucleus together. Einstein's famous equation, E equals mc squared, relates directly to the calculation of this binding energy, the energy that holds the protons and the neutrons together. Nuclear fission is a way that we can gather energy. It is a process where large atoms split into smaller atoms, and it will generate huge amounts of nuclear energy that can then be transformed into eventually a mechanical energy. It is carried out in nuclear reactors, and it's the same energy that it was released in the atomic bomb. In the visual down below, you can see basically what happens is we take neutrons and we collide certain atoms with those neutrons. It causes the nuclide to split apart into smaller pieces, and it also releases neutrons in that process, in which those neutrons then find other atoms that they will collide with, and we continue to get this process of splitting atoms into smaller and smaller atoms and providing huge amounts of energy. The bombardment of the radioactive nuclide with a neutron starts the process. The neutrons released in the transmutation strike other nuclei, causing their decay and the production of more neutrons, and this eventually goes on and on and on, and we call this a nuclear chain reaction. If there are not enough radioactive nuclides in the path of the ejected neutron, the chain reaction will die out. Therefore, there must be a certain minimum amount of fissionable material present for the chain reaction to be sustained, and that is called critical mass. As mentioned, these type of fission reactions occur in nuclear reactors. The heat generated by the reaction is used to produce steam that then turns a turbine connected to a generator, and we end up getting power. Here you're taking a look at a picture of the reactor core inside the nuclear reactor, and the reaction is kept in check by the use of something called control rods. These block the paths of some neutrons, keeping the system from reaching a dangerous supercritical mass. As our non-renewable resources are being depleted, such as fossil fuels, it is important to look to the future, and nuclear power plants seem to be that future for us. But there are some drawbacks. Hazardous radioactive fuels and fission products are being produced, and right at this point in time we have a hard time storing them and knowing what to do with them at a later date. There is a limited supply of uranium-235, which is the main supplier in the control rods, and we don't know where to put those spent fuel rods. They require 20 half-lives to decay to safe levels. The other process is called nuclear fusion, and this is where smaller atoms combine to form a larger atom. At this point, nuclear fusion occurs in the sun and the stars naturally, and it generates huge amounts of energy. It requires temperatures of 40 million Kelvin, and we have found that we can achieve this by an atomic explosion, but obviously that's not very safe. We don't have the materials capable of withstanding these high temperatures, and these are the drawbacks to nuclear fusion, and that's why we are using nuclear fission right now as a way to produce nuclear energy. Nuclear fusion would be a superior method for generating power. The good news is that the products of the reaction are not radioactive. The bad news is that in order to achieve the fusion, the materials must be in that plasma state at several million kelvins. The tokamak apparati that you see up in the upper right-hand corner has promise for carrying out these reactions. They use magnetic fields to heat the material. We look to the future in hopes that nuclear fusion will be a way that we can produce nuclear energy. Only time will tell.